1 minute.
Problem 11.
Problem 11. Do you accept? Yes, okay. Time is for presentation. Okay. Please write down your name on the blackboard. Honor. Write your name. Okay, reporter, take the floor.
Okay, so honorable viewers and fellow participants, I am the reporter of Team Trivial, and today I'm going to report problem 11, pumping straw. So the problem statement is as follows. A simple water pump can be made using a straw shaped into a triangle and cut open at the vertices. When such a triangle is partially immersed in water with one of its vertices and rotated around the vertical axis, water may flow up along the straw. So we need to investigate how the geometry and other relevant parameters affect the pumping speed. So based on the problem statement, I will say that the key point is the x velocity of water and the geometry of the straw. So now let's take a look at a few parameters. The first is the rotation angular velocity of the straw system. And second is the straw diameter. And also the side length of the straw. And the depth of immersion here. So here you can see that this is the very bottom of the straw. And this horizontal line here means the water surface. So it's the depth of immersion in the water. And also the tilt angle, which we take to be around this angle here. So if it's a equilateral triangle, then it will be 60 degrees. And also these things are sort of related. So they all describe the pumping speed. So for example, the exit velocity of the water here, and also the maximum range, which is the distance water droplets emerging from here and the beach. So here's my experimental setup. First, I use a camera here to capture the motion of water droplets here, and also to record the angular velocity. And I place rulers on the ground to measure the range. And here's my main setup. I use a power supply to give power to the motor, which is connected to the straw. And this water supply and the bucket here, there's constant water going in the water supply. So the water surface will be constant at all times. So I also made a lot of straws with different geometries to investigate the parameters. So for the qualitative theory, let's consider a very small water segment, and this segment is accelerated due to the centrifugal force, which is given by this equation. And we see that it is proportional to r, which is the radial distance. So which means that water at higher positions will tend to accelerate faster. Now it's because of this difference in acceleration, so we see water droplets coming out and not a water stream. So for the quantitative theory, let's consider some dynamics of the infinitesimal water segment. So here we consider the radial position from the axis. And this infinitesimal segment is subject to two forces. The first is the gravitational force mg, and the second is the normal force given by the wall, which is N. Now, we can write down the Newton's second law equation and in the coordinates of r hat, theta hat, and z hat. Now, we can separate it into different components. So this is the ma in the radial direction, and this is the force in the radial direction. Now, solving this differential equation, we can get the equation of motion of this infinitesimal water segment. Now, here I have used the constant r0c, which is defined here. And the meaning of it is the minimum initial radial distance for rising motion to happen, as you can see with the cost function here. So here, based on this equation of motion, I can calculate the radial distance and set it equal to the radial length, which is this thing here. And I can calculate the time that the water will leave the straw, which is given by tau. I know that's tau. And given tau, and we can differentiate the radial velocity to get the exit velocity, which is simply v at tau, v of tau, which is given by this equation. Here you can see that the height of the water segment, h of t, as a function of time, will increase, and the increase is getting higher and higher, so acceleration is increasing with time. So here, because we are dealing with the fluid and not a point mass, we have to correct it using some other factors. So for example, the viscosity is given by this equation. Given the average flow speed and the diameter of the straw, we can calculate the pressure difference. Now, if we calculate the Reynolds number of our flow, we see that it is above 10,000, which means it's a turbulent flow. So we have to use this equation to find the coefficient Fd here. Now, you can take a look at this graph. The correction of viscosity will reduce the exit velocity. However, the difference is not significant. It's only to around 0.0005 meters per second, not very significant. Now, for Bernoulli's law, we can apply the Bernoulli equation at this point and this point, denoted by light blue and yellow. So you can see that the correction is very significant, and at higher angular velocity, the correction is even more important. So we can correct the surface tension by approximating it as this force, which pulls the water upwards. Now, we can define an effective gravity, so we have all those forces, and they all cause a different acceleration. So if we combine all of them and divide it by the mass, we can get an effective acceleration, which I will call the effective gravity. And plugging this into our point mass model, we can figure out the motion of water. So another factor is air resistance. So if we calculate air resistance based on this formula, we can get that change in air resistance. Due to air resistance, the velocity change is around 2.3. However, this air resistance is based on a lot of factors. For example, if we want to solve it, we have to solve this differential equation, which is very difficult. So I just fitted the delta VD, which is the velocity difference due to air resistance, about 2 meters per second, determined by fitting experiment. Because if we fit this value into our experiment, they all match. So this difference is around 2 meters per second. So how can we verify the experimental? Well, we can use basic dynamics to find the relationship of the range of scattered water droplets with the exit velocity, which is given by this equation. So if we compare this with our theory, we can see if our theory is correct. So for the experiment, the process is I use a high-speed recording iPhone 240 FPS to record the angular velocity, and I measured the scatter range with the ruler and then compare with theory. So here is the effect of immersion depth. On the left and right, you can see that the effect is not very significant. I have these are 3 different immersion depths at 5, 15, and 25 millimeters. So a larger depth will give a large higher V, but it's not very significant. And you can see here that the theory and experiment match. So here's the effective different straw diameter. The straw diameters are 4 millimeter, 8 millimeter, and 12 millimeter. So because there is surface tension that pulls the water upwards, if the straw diameter is smaller, then the surface tension is more significant, and the exit velocity will be higher. So a smaller diameter will have a higher V due to surface tension. And for the effect of different straw diameters, you can see that experiment and theory agree. So here is the effect of different tilt angles. So here you can see that we have done 2 cases. The first case is for phi equals 30 degrees. So phi equals degrees means the top angle is 120 degrees. So it's the blue line. And the red line is phi equals 60, which is a equilateral triangle. Now, you can see, sorry the colors are different. The red line here corresponds to phi equals 30, but here is the blue line. So the trend is the same. And you can see that experiment and theory also match. So here we discuss the optimal tilt angle. So the tilt angle is phi. And if we plot this, the exit velocity is given by our previous theory, which is this formula. And it is a very complicated function of phi. So if we plot this function as function of phi, you can see this curve. So if the tilt angle is very large or very small, that is if the straw is very flat or very acute, then the edge cases is that the moving speed will be low. However, at a very critical angle, the exit velocity will be the largest. So if we want to design this for practical purposes, this should be a meaningful discussion. So for the conclusion, we first use the point mass mechanics to determine the radial distance of an infinitesimal water segment as a function of time. And then we correct it using various factors such as viscosity, surface tension, air resistance, and Bernoulli's law. Now, based on our theory, we can get the exit velocity as this equation. And by measuring the scatter range of the water droplets, we can determine the experimental exit velocity. And we can compare these two to see, and we found that the experiment and theory match. So here is a conclusion of different factors. So for viscosity, if the pumping speed is smaller, if there is viscosity, the pumping speed will be smaller, which means the exit velocity will be smaller. However, this is insignificant. Now for surface tension, if there is surface tension, then the pumping speed will be larger because the surface tension pulls the water segment upwards. Now for Bernoulli's law, because it predicts a pressure difference, and the pressure is higher at the bottom and smaller at the top. So if we consider Bernoulli's law, we will get a larger pumping speed. Now for air resistance, which we only approximated, it will cause a less stronger range, which we measured experimentally, and we corrected it based on experiments. So here is a conclusion of all the different factors influencing this phenomenon. So if we have a larger immersion depth, we will have a larger exit velocity, but we found that it is not very significant. And these three are the ones that actually affect the pumping speed. So first is the higher exit velocity, which we can observe by our previous plots. A higher exit velocity or a smaller tube diameter, and at a critical tilt angle phi, we will all get a larger exit velocity. So that's the end of my report. Thank you.
Thank you. The appreciation from opponent.
What do you think is the pumping speed?
Yes, so pumping speed. There are various definitions. I think they're all equal. So you can say it's flow rate, it's the exit velocity, it's the range that it shoots.
So in your experiment, what are you talking about when you're talking about the pumping speed?
Pumping speed.
Because in one of your graphs, you talk about the pumping speed with an optimal angle.
Yes.
And I'm curious to know what is the definition here of pumping speed?
This is the exit velocity.
The exit velocity of when the water gets out of the straw.
Yes.
Okay, so it's not the fluid.
There are it's a simple correlation. You just multiply by the area.
Okay. So here you consider the forces of the angular velocity.
Yes.
Is it a fictitious force?
Fictitious force?
Fictitious force.
Well, it's a rotating system, not a linear accelerated force.
So is that force an imaginary force?
It depends on the specific coordinate system. Are you talking about the inertial coordinate system or a non-inertial?
So what coordinate system do you use when you're because you're trying to measure the R?
If I use this equation, it means it's inertial.
Okay. So you use your accelerator Okay, so in the figure here, what do you think is the velocity of fluid right here?
0.
And the velocity of fluid here is the exit velocity, like
yes,
just stated.
yes.
So you did not consider continuity when you're doing this here.
I mean, the area is the same. Right? Yeah.
Okay. All right, that's 3 minutes. Preparation. Okay, opponent take the floor.
Okay, Fury and fellow contestants. I am the opponent of the Lagrange team, and I'm reporting on number 11, Armstrong. And here is the problem statement. Well, I think the most important part of the problem statement is the geometry or relevant parameters affecting the pumping speed, which I think the definition is actually the flow rate of the pump. Okay, this is their report's outline. They have the problem statement, and they have considered several theories like the angular velocities, the fictitious force, and Bernoulli's law, and the viscosity of the fluid, and then did an experiment and to find their correlation with the theory. Here is the summary. They use the range of water spilled out to calculate the exit velocity of the water, and then find the pumping speed through the theory, and they try to make a correlation. Then they experiment with different angles of straws and the geometry of the straw. And here is the report. Well, the strength is that they have considered many different angles and have considered the immersion depth of the straw, and also considers the optimal tilt angle, meaning that the tilt angle which the exit velocity is the largest, and also considers different angular velocities. Well, there are some areas of improvement, like how their theory fails to account of continuity. Well, I think Bernoulli's law accounts for continuity, but your theory on angular velocity doesn't. So I think it's a little bit vague, and I hope you can explain it later. And I think in your experiment, if you use a motor to turn the straw, you should discuss the precision of the straw, because it kind of wobbles. And the straw thickness should also be listed as a variable, and you can use different straws to measure the pumping speed and what is effect on the pumping speed. Also, if the experiment does not account for inertia on the effects of different straws, meaning that when they changed the geometry of the straw, they didn't consider the inertia's effects on the experiment. Okay. Now for some points to clarify is how is the angular velocity measured and how is the range measured. We can start our discussion. Okay, so how is the angular velocity measured?
So here we have a camera recording at 240 FPS.
So what kind of software do you use?
Yeah, I use Tracker.
You use Tracker to find the angular velocity. So does it always stay the same throughout your experiment?
I changed the power supply's voltage.
So I mean, in one experiment, does the angular velocity stay the same throughout the time frame?
Yeah, because it's constant for both voltage.
So what time frame do you choose?
I choose it after I change the voltage because.
I mean, what time frame do you choose when you're shooting the experiment, right? When you put it in Tracker, you use a time frame to calculate the angular velocity, average angular velocity.
I just count how many frames and how many rotations.
I mean, how many seconds? How many seconds do you calculate?
Seconds. Yeah, I think I did 40 rotations.
40 rotations, and you calculate how much water got out or ejected?
No, I calculate how much time the straw rotates in 40 times.
Okay, and how do you calculate the exit velocity with the range?
Yeah, so you see the straw is here, right? And the droplets will go out and hit the floor. So there's a ruler here.
So it will be like a circle around the
Yes,
experiment
yes,
setup?
yes, it will be so.
Well, zero negative roughly. So the experimental setup is something like here, like this, right? And this is the range,
Yes.
indicating that this is like a circle around it.
Yes.
So do you think the flow is shoot out like this
No.
or this? When the straw is here?
Where's the open?
I mean, when the straw is, does it shoot out here, or does it have a vertical angle with the angular velocity?
I
I mean, it'll shoot out of here, or
yeah, control the velocity. Yeah. So the straw is like this one. So there are two components of velocity. So the first, of course, is the velocity along the straw. And we have calculated this is V. Now, the straw rotates, right?
And in what direction does it speed?
Yes.
Is it here?
No, it's not it. Because if it rotates,
Yes.
so there's a velocity.
Yes.
So then if this R, then this will be an additional velocity. Yeah, so it's not a.
So it's something like this.
Yes.
Okay. It's something like so.
Yeah, it will look like that.
So how can you calculate the range?
Yeah, so you see, this is a combination of two velocities, right? The first is V, and the second part is this. So this doesn't affect the range, it just swings around. Yeah, you can see it separately. And this is what changes the range, and this is sideways.
Okay.
So the sideways doesn't affect the range.
So it doesn't affect the range. You can still calculate with the theory that.
Yes.
Okay, I understand. So when you conduct the experiment, in the early stages of the pumping straw turning, will the water reach the set range that you have just measured?
I didn't observe because there's some time for me to turn up the voltage and go there to measure. So I didn't measure if they did it.
So I think in the early stages of the experiment, you can turn to page 9. Okay, this is your theory, right?
Yes.
You have considered the forces acting on the water here. Okay, what is the end here? Is this the water above the water surface, or
No, just the mass of this very small segment.
so in the early stages of your let's say pumping process, this will have no continuity since it is zero here and they have a exit velocity out, right?
Yes.
But if you said that you need some time to get here and turn on the camera, it will go over some time. The pumping process will turn to be stable.
Yeah.
And when the pumping process is stable, you should take account of continuity in your equation.
Yeah. So you think the speed entering should be the speed exit?
Yes, the continuity should
Yeah.
work. And does your theory have consider that?
Well, because we say that there is acceleration, right? And
Yes.
if it's acceleration, the velocity cannot be the same in every location.
Well, because it's a fluid and it's pumping at a stable rate. So do you think that continuity will have something to do with your equation, or do you need to modify your equation if this happens?
I don't think continuity is essential because you observe the water droplets coming out. They're droplets. They are not stream of water.
So you think that there are something like this, that little objects that are moving out
Maybe till the end. Maybe until the end.
to the end. So,
Yeah,
so you cannot calculate it that way because it only appears as your theory at the end of the straw. But when you see, because have you ever turned down the indirect velocity to make the straw stable, make the water level stable?
Not we cannot do
Well, if you do this, you will find that this is a complete water flow, meaning that you need to take account of continuity when you're doing the experiment when the water spills out.
So you said it's a continuous flow, right?
It's,
Yeah, but is there velocity here?
there is no velocity here, and the fluid stays in straw stable
Yeah, so
when you're doing a static examination.
yeah, so it's not the flow, right?
So how do you prove that you don't need to take account of continuity when I say it is turning and spilling out the water?
Well, I think if you want to consider continuity, then there must be some velocity at the bottom.
Yes.
And I didn't include that in the theory. So yeah, I think
So it should be bottom.
yeah.
Okay, and next page. So, the page of Bernoulli's law. And okay, this is the viscosity correction, right? So you listed out many theories that may change your experimental results.
Yeah.
Have you ever tried to try normalization of your theories to find out which affects the most? Because your experimental results and yes, what are the correlation between your theories and your experimental results?
I'm not sure the plot. In the comparison?
Yes.
Yeah, I think I have one more plot here. Yeah, the dotted line is theory, and it's circle dots and connected. They are experiments.
Okay, so the theory here is the angular velocity that we have just talked about.
Yeah.
Right. So you say that this is a linear line.
Yes.
Okay. So in this place here, you didn't consider the viscosity or.
No, of course I consider. This is considering everything.
So this is considered the Newton's law, viscosity,
Surface
and
tension.
surface tension. Okay. So now we go back to your experiment here. So this motor, do you think there will be precision in this motor, meaning that it will wobble while pumping the water?
I think I have to explain it a bit more. Do you think it wobble?
I think it wobbles a little bit.
Yes, but do you think that affects the experiment? Because the contact position, I think it remains the same. Or if it's not obvious.
Okay, you can make your points. And in this video,
Yes.
you can see that there are waves.
I mean, the water.
Yes. Does this affect the fluid flow under the pumping straw to change the experimental results?
I think the important thing is the immersion depth, right? So as long as the flow, the wave, or even the wave created by the straw.
So it does. So it is about its correlation with the immersion depth of the
Yes.
straw. And can I ask why is the graph of your data linear?
Linear. Okay. So basically your question is, we have exit velocity, right?
Yes.
Okay. So we go to exit velocity. So okay. So what you want to ask is why is V linear to omega, right?
Yes.
So you see that this term here, So this term here doesn't have omega, right?
Yes.
And here's
Okay, so you have your
yes,
and
but
does the slope equal to this?
experiment, yes. Yeah, experiment, yes.
So have you tried to analyze your slope in your experimental results?
The slope, like as I said, if we put them side by side, you can see that the slopes are almost the same.
So can you analyze the
I can do a regression.
yes?
Yeah, of course. But I think just putting them here is proven.
This process. Okay, in here you can, so your experiment, does this match up with the theory?
Yes.
I'm not quite sure what this graph.
So basically, if you combine these two, it will be this. The dotted lines are the same. Yeah, dotted lines.
So when there is a very little omega,
Yes.
there might be some difference between your.
Yeah, that's a special case.
Why does this happen? Can you talk more about it? What variables might cause this to happen?
Very small. If you take a look at other experimental plots.
This tends to happen. Can you explain why when omega is small, this happens?
So the experiment is lower than theory. So, do you have any idea?
Okay, well, I think when omega is small, the water will.
Okay, time's up.
Okay.
Gordon, summarize.
Okay. The reporter has talked about many interesting theories that were newly saw, the centrifugal force and the surface tension and viscosity. Well, I am still questioning about whether the centrifugal forces theory is correct here, since it lacks the counting of continuity. And we have also gone over on how their experiment is conducted, and knows that the angular velocity is measured through tracker, and the range is used to measure the exit velocity of the water in the straw. Also, we have gone over relevant parameters that might affect the pumping speed. like the angles of the straw, and like how the omega changes. However,
Okay.
the omega is still.
Time's up. Questions from review.
Okay, this question is for the reporter and the opponent. So what do you think is the most important variable in this phenomenon?
The angular velocity.
The angular velocity experiment.
Okay, so, I want to ask both of you, does Bernoulli principle affect a lot in this phenomenon?
Yes.
Well, yes.
Okay, and can, okay, so if you use, okay, again, use the blackboard. So if you want to use the Bernoulli's principle, the water, here's a straw, but the water needs to be full for to use Bernoulli's principle. And if it's not full and like this, it's not a stable flow. And why do you think you can use the Bernoulli's principle?
So my first, you just have to use it on the same flow line, the stream line. Yeah. So I don't think the water has to be full. It just has to be one particle and one flow line.
So do you think this is a steady flow? Do you think this is steady flow?
I don't understand why the water is.
So you think that does the water fill up all the straw or only the bottom part of the straw?
No, it doesn't fill the water.
So it fills every part of the straw.
Yes, but it emerges as droplets. At the end it becomes droplets because it's
Yeah,
a little.
so that's not a stable flow.
At the end, yes.
And what does the opponent think?
I think on a unit should be more. And Bernoulli's law certainly does work in this circumstance, and I think that they should do an experiment to shoot this moment.
Okay. And my next question is there? Do you think there is a critical omega for to spin to pump?
Because the condition is that it has to pass through the height of the straw. Right? It has to pass through this. Yeah, so yeah, it is.
Okay. Do you think there's a critical omega?
I think because according to the theory, as the omega increases, the exit velocity also increases as well.
Okay. So when omega is 0, would it pump?
Oh, of course not.
Okay. So if the setup of this phenomenon is like this, but if we do only one side, what would happen?
The rotation is not stable.
Let's say the motor is very strong and stable.
One side. I think it's the same.
Well, not considering position of this, the pumping speed will be half of the what it is.
Okay. So you change the voltage of the motor, but did you consider there's a water resistance inside this? So that would change this.
I measured the angular velocity from video, so of course they considered the resistance from water.
Okay, time is up. Review prepare for 2 minutes. reviewer, take the floor.
Okay, hi, I'm a reviewer for team relativity. So here's a common statement. So a single water pump can be used to make a triangle shape, and if it cuts out in the vertices, then rotate around its vertical axis, it will be water flowing out. And then the reporter needs to investigate how the geometry and other relevant parameters affect the pumping speed. So here's a quick summary of the report. So he talked about the centrifugal force, and then his critical angular velocity for pumping up the water, and then his pumping speed. But I think the pumping speed in his presentation could be different. And then his extraction of water, and he considered his viscosity and air resistance, and then produced Bernoulli principle to explain his phenomena. And he has a lot of different parameters, and instead of he uses a motor that can control, and then use a high frame camera. And the reporter, I think he has a lot of experience to prove, and then he has a good assumption. And he has a well modeling on the straw itself, and then he considered a lot of parameters, including viscosity and air resistance. But I think the measurement could be better, and then he didn't explain the definition of pumping speed, and then he has some ground physics equations. And Poland, I think he knows the correct definition of pumping speed, which is very important according to the problem statement. And then he has clear and key question asked, and then know the situation where the Bernoulli's principle could be used. But the suggestion is he has some bad time management on short question, which takes too long on a single question. And then when he talks about his key question, he didn't continue the discussion on it. And then so here's the first discussion. So the opponent asked, what's the definition of the pumping speed? And the reporter said it's exit velocity and with water pumped out is all correct. But in my opinion, I think it's a definition. Pumping speed is about how much water is pumped out, the volume of water pumped out in the time. So it's the pumping speed, it's not the velocity out of it. And then he also asked, how did you measure the angular velocity? And of course that he uses a high frame camera to use it, and I think it could use a better weight. And then Plan asked, does the water go up small amount or a whole straw? And then the reporter said small amount, and I think he should maybe show some more clear experimental video to show. And then I asked both the reporter said what affects the motion the most, and the reporter said the angular velocity, and the problem statement says maybe the geometry could be more considered. And then these are the missed points of the discussion. So the first is about the pumping speeds, and I think that they should have more discussion about the pumping speed, because the pumping speed the opponent said is correct, but he didn't talk that much in his discussion. But I think it's very important because the whole problem statement is asking about pumping speed, and the real definition of a pumping speed is how much water is pumped out in a single amount of time, and it's not about its exit velocity. And then I think the opponent should ask the reporter about more on his measurement, because I think there will be a lot of difference. There will be some errors in his measurements. And I question on the water stable, because according to Bernoulli's principle, the water needs to be very stable for it to use the Bernoulli's principle. But in my consideration, I think the water flow on the straw I drew before isn't stable, so it maybe can't use the Bernoulli's principle in this situation. And that's my presentation.
Okay. The reporter make the concluding remark.
So first, I would like to talk about the exit velocity. So the reviewer has said that we talked about the exit velocity. So I think it and the pumping speed are related, because this times the area is equal to the flow rate. So I think they're pretty much related, and you can interchange between their argument. And okay, so given the continuity equation, there may be flow speed at the bottom of the straw, and we should take that into our consideration. And there exists a critical for omega, that is the angular velocity. And we also discussed why the depot is approximately linear to omega. And here, we also talk about that the exit velocity has two components. The first one is along the straw, which we calculate with the and the second one is due to the rotation of the straw, which is r cross omega. But since the latter is only in the rotating direction, the former is only the former accounts for the pumping speed, and we don't need to worry about the droplets swinging. And the measurement of the angular velocity is done with a video. And it's not some conversion with the voltage. So we have considered the straw there may be friction forces from the water to the straw. And also, a large amount of our discussion is based on the Bernoulli principle. So I think the Bernoulli principle can be used as long as we are analyzing a streamline. So I'm not entirely sure what the reviewer meant about a stable flow, but as long as we are analyzing one particle and at two positions, I think we can use Bernoulli's principle. Thank you.
Okay. Now, question on 9.
Question for the reporter. At some point you mentioned that the zero number was too high, so the flow was kind of turbulence, right? So would that be good for you to say, was this Bernoulli's equation blah, 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 to make this fit?
I think as long as we are analyzing 2 points in the straw in the water, I think we can use Bernoulli's law.
I think Bernoulli's law can also be used to analyze the airflow above the straw, which might also affect the liquid that is inside the straw.
I don't think the phenomenon is a steady flow, so the Bernoulli's principle can be used in this analysis.
Yeah, the reporter, why does it, is this a critical angle? Why it can be why?
So because the angle has a lot of different effects. So if the tilt angle is larger, the gravity is more important. And if the gravity pulls it down more, it's harder to get, the water harder to get out. So at very high tilt angles, there is a very low moving speed. Now, if the tilt angle is very wide open, then so there is a different boundary condition for the water, and the moving speed will also be low.
So if you shrink your diameter of your straw tube, what will happen?
I mean, I increase or
So shrink, reduce.
yeah, if I reduce the surface tension will be more important. So the pumping speed will be larger.
So within the surface tension will enhance pumping speed.
Yeah.
Optimistic.
Yes, I also agree with the reporter about if it's thinner, the surface tension will be bigger and will be harder to pump out.
Harder to pump out, but he said enhance the pumping.
Well, the pumping speed is talking about the flow of water per second. So when you shrink the straw diameter, the cross-section area of the straw decreases, which will make the pumping speed more little. Decrease.
So that I think that's the definition. I think he's talking about this
Except velocity.
the velocity.
But you asked.
Enhanced.
Yeah, I agree with the point. We should consider area Q.
Okay.
I was talking about it.
Okay.
Now, question for the viewer. At one point you were asking the using one side of the straw. What's your point? You were asking if use only one side instead of. What are you trying to ask?
It wouldn't be stable if you only want to use one side.
Okay.
So maybe the question is for the reporter. So could you describe how you experimentally get the S6 velocity?
So all I can measure is how far the droplets go. So this one, right here. So you can see I draw this line. So it means that the droplets will go in parallel. If we don't consider air resistance, and we can measure this range here, the R. We measure it with rulers, and we can use basic dynamics. So basically, half gt squared minus v sine theta, and we use that to determine the fixed velocity. So it's just dynamics.
So maybe a further question. So at some point you described that when the water hit the pipe,
Yes.
there is another component.
Force, velocity.
Yeah. So and you argue that this velocity will not affect the distance the water droplet travel.
Yes.
Were there any contradiction?
No, because only this component will affect range. And the rotating component, because it's going in circles more.
So what's your opinion about this statement?
So I think it will affect the range. When you consider the diameter of the straw and the big range, it is from every point of this small circle, meaning the small straw is big, and it has a way to go to the big range, and this could affect their results.
Yes, and I agree with the opponent, it would change, yes.
Okay, thank you. And I think we stop here. Please see. Okay, for the reporter. Nine 587. For the opponent, 88675. For the reviewer, 99877. Okay, and we will conclude our